This is a standard parse tree being built by a method called recursive descent. To process code, the parser attempts to grow this tree from the top down, but it relies on guesswork. If it picks a rule that doesn't match the input, it hits an error, kills the branch, and retreats to the root to start over. This is backtracking. The parser makes a choice, realizes it's wrong, retracts the work, and tries again. This cycle of trial and error consumes significant computing power. Across a large program, these failed guesses create a major bottleneck that slows down the entire compilation process. Modern compiler design requires a more efficient architecture, one that identifies the correct rule immediately, eliminates recursive loops, and never has to backtrack. Replacing guesswork with mathematical certainty requires a system of foresight. This is the logic behind non-recursive predictive parsing. To give a parser foresight, we first need to extract specific rules from the grammar. We begin with a tool called the first set. The first set identifies the specific terminal characters that are legally allowed to begin any string generated by a rule. In this expression, the set isolates ID and the open parentheses as the only valid starting points. This gets complex with epsilon, the empty string. If a primary symbol resolves into epsilon, it disappears. The parser moves to the next available symbol, using its first set to determine the starting character. By mapping these sets, the compiler can predict exactly how any grammatical structure will begin before it even processes the code. While the first set handles how a structure begins, the parser needs to know the legal boundary where it ends. This requires a second tool, the follow set. The follow set identifies which characters can legally appear immediately to the right of a variable. In this rule, because B is positioned directly after A, it is the only valid member of the follow set for that variable. To manage the end of a file, compilers use a specific anchor, the end marker. By definition, this $sign is always placed in the follow set of the program's start symbol, signaling the parser has reached the end of the input. By combining first and follow, designers can remove ambiguity from the parser's decision-making process. Once we have these mathematical sets, we organize them into a deterministic database, the predictive parsing table. This table acts as a decision matrix. The non-terminal variables form the rows, while the terminal characters, including the end marker, form the columns. We use the first and follow sets to populate the grid, slotting each rule into the intersection where it is mathematically valid. With the table complete, we can use a non-recursive stack-based parser. This version uses an internal memory stack rather than complex recursive function calls. To parse, the system compares the stack's top item against the current input symbol. It finds that intersection in the table, replaces the stack item with the correct rule, and checks for a match. When they match, both are cleared, moving to the next character. Because the table eliminates guesswork, the parser correctly identifies the structure on the first attempt, proving the grammar can be parsed with complete foresight. We have now moved from the chaotic, resource-heavy nature of backtracking to a single, highly efficient stack operation. This creates a sequential pipeline for modern compilers, turning a grammar into sets, the sets into a table, and the table into a predictive parser. The elimination of backtracking changes the efficiency of the build. Because the parser never has to rescan or re-guess, it can process the entire source code in a single direct pass. However, this table-driven method isn't universal. It raises a question: does this matrix work for every type of programming grammar? It doesn't. This specific pipeline only works for grammars that follow a restricted set of mathematical rules, known as LL1 grammars. Predictive parsing solves the bottleneck of wasted time, but it requires code to conform to the strict laws of LL1, forming the foundation for how we design modern, high-speed compilers.